Naveen sir, can you unmute and let's start?
Yeah, hello.
Hello. Yeah, yes sir, let's start.
Yeah, give me 1 minute. I'll start.
Yeah, sure.
Yes. Am I audible? Hello.
Yeah, yes sir.
Yes. Okay. Let me start. Okay. Okay. Good evening, guys. So, welcome to our fourth session here. In the previous three sessions, we have completed 2015, 16, and 2017 paper one, and then set one. And today we are going to discuss 2017 set two. Okay, in the production and manufacturing point of view. Okay, I mean, this set two is having some little good questions as well as little lengthier than the previous ones. So let's go and discuss each question in depth. Okay, so yeah, this is the question that has been asked. Which one of the following is false? Please try to understand this is false. So that's very important. So you have to know one is false and other three are true. So, so let's go one by one. Whether the statement is true or not, then we'll write T. If it is false, we'll write F, and then we'll take the right one. Okay. The number of taps generally used for hand tapping is 3. So if you know tapping, then it would be very easy for you. This is called tapping process. Right? Let me take some other ink. So this is tapping process. When tapping is used after drilling or after making some holes, because drill bit will make hole good. If you want to maintain the surface roughness of the hole, you have to do this tapping process. It's kind of a grinding process, you can say. Okay. So generally, if you do some machining like milling and all, you do the grinding, right? For the flat surfaces or for the cylindrical surfaces, you do the grinding, right? In the same way, if you have an internal hole and you want to make it smoother, then this is the process that you have to use. And what is that? The option they have given is the number of taps generally used for hand tapping. So this tap that you're seeing is hand tap. With hand, they'll be inserting, and you might have seen they'll be rotating it, right? That is what is hand tapping, right? So if you see here, obviously it is right. Okay, it is true. The number of generally used are 3. What are the 3? Taper tap, plug tap, and bottoming tap. So that is the reason why this is right. But we are going in depth and discussing what are these 3 different types. Maybe they'll ask the next question. Maybe they'll be asking in depth what is the speciality of plug tap or taper tap or bottoming tap. Okay. So in taper tap, generally we have, okay, the important part here is the chamfer. So this zone, the entry zone, this is like after that, it's okay, it is common thing. But this is called the entry zone, and that is chamfer. Chamfer is nothing but kind of a, angled thing. Okay. So there are 9 threads here. There are 5 threads here. There are 1.5 threads here. So this can be a question. Maybe they'll be asking how many threads are there on plug tab. So when are they used also can be a question, isn't it? So we can say, so the initially when this is the procedure, the progress is taper tab, plug tab, and bottoming tab. Okay, what is the difference? Okay, generally once hole is made, then what we'll do, we have to make it a little smoother. The inside hole has to be smoother. Okay, now what you will do, you put the tab inside, you rotate it, you keep on rotating it. As you keep on rotating it, the material will be removed in the form of small pieces. And then generally this is used for uh, normal holes, in the sense like used for it's used for open, and I mean generally this tapping content is used for blind holes. Okay, blind means like hole which is blind. Okay, I'll have to draw the diagram then. Should have put the diagram, but anyways I'll draw it. So if your hole is like this, it started here and it ended here. So this is called blind hole. Can't see the other side. You're blind to the other side. Through hole is through which it is going inside. Okay. So generally this taper tab is used in through hole applications. It can be used for blind holes, but generally this is used for through holes. And here again in plug tape, we have 5 threads in the chamfer region, right? So again the same thing, right? You put it, you do it, and generally this is used for blind hole applications. Generally, in general, but I'm not saying here in taper tape we will not be using it for blind holes. It can be used, but very limited applications are there. Okay, in urgency, you'll be using it in the starting stage. That's it. So this is for blind hole applications. Blind hole applications. Okay. And bottoming tab is having 1.5 thread chamfer region, right? And this is generally used for blind holes only after, if you are able to not get that kind of an achievement with taper tab or the plug tab, then you'll go to the blind hole, I mean, bottoming tab chamfering, I mean, bottoming tab tapping. Okay. So this is for generally for blind holes, but you have to go inner. You have to go a little blind hole in the sense like you can't see, right? Maybe it is very deep in nature. So if you want to explore the inner regions of the hole and make it smoother, then you have to use it. So it is like I can say that get close to the inner region or get close to the bottom of the blind hole. These are the tapping things. 3 taps are there, very important, hand taps. Okay. So obviously this is right. There is no problem in this. This is true. Right. Pispan model in machining is used to estimate shear strain. Obviously, whoever studies machining, we have to go through this Pispan model, right? And this Pispan model is written. I mean, the figure that you are seeing in the right hand side bottom is Pispan model. What is that? We'll discuss. This is okay. Span model. So what are they saying? They are saying that we use for estimate shear strain. Yes, yes, it is used to estimate shear strain only. Okay. So why? Because you see here, this is your shear angle, right? This is your shear angle phi. What is Pispan model? It's nothing but deck of cards. Okay, let me remove that phi and we'll discuss. So these are deck of cards actually. Card 1, card 2, card 3, card 4. And suddenly you have put some kind of an obstruction here. And that is what is tool here. Okay. Now what happens? The deck of cards start moves in the direction of the face of the tool. And you see the direction is being changed at this angle. It can happen at any angle. If you're doing faster, maybe it'll have no, don't think this is perpendicular. This is not perpendicular. This is not perpendicular. Wrong. You might ask, sir, it is like this. No, this is perpendicular. No, it is not perpendicular. That is the thing. Okay, it is not perpendicular. So it can take any angle, and that angle is what is called here shear angle. And for measuring the strain, the estimate shear strain, if you want to the shear strain, it is cot phi minus alpha plus cos tan phi something. I don't remember the formula. That is the formula, right? So you want phi, you want shear angle for that. You want shear angle for that. Okay. So that is the reason why Spanner model is important, because to estimate the shear angle, and after estimating the shear angle, you'll be able to find out the shear strain. So obviously this also is true. Okay. Chip hammering during machining is due to improper chip control. First, we'll understand what is chip hammering, then we'll see it is because of improper chip control or not. Okay. What is chip hammering? Chip hammering is nothing but, let's say you have the tool like this. Okay. This is tool, cutting tool. Now what happens? As you are machining this side, the chips will come like this. The chips will form like, okay, chip, I'll take it in different color. Chips will come like this. And you understand that based on the feed, depth of cut, and the width of cut, the chips will have its own morphology. It's called chip morphology. The color of chip, the thickness of chip, the curl of chip. Curl of chip. In the sense like how curly it is. Right? Curl of chip. Now what happens? As you are trying to proceed with the machining operation, the chip curls back. The chip will curl back and hit the tool again. That is not good, right? The phenomenon where the chip is curling back, hammering into the workpiece or tool, right? This curl back of chip and hammering back into or back into tool, back into tool. That is where hammering is happening, right? Why it is happening? Because of you're not controlling the chip direction, chip flow direction. You're not controlling. If you would have controlled, this curling back would not have happened, right? So that is the reason why hammering is happening. Chip hammering due to machining is due to improper chip control. This also is true. And what is the option that is left out? This is the one. Of course, this is the wrong one. And for our question, this is the right answer. But the statement wise, it is wrong. Why? We'll see. Cementite carbide tools are generally or in compression. You see, first we have to understand why it is. What is cemented carbon? Actually, cemented carbon is known for its excellent hardness and wear resistance. Good for hardness and wear resistance. If you know this, then statement makes nonsense. So what is hardness or wear resistance? the ability to avoid, or the ability to sustain an indentation. Indentation means some compression. If you are able to indentate some material, indentate means pressing, putting some edgy object and pushing it. If it is uh, failing, or if it is having some dent easily formed, then it is not hard. If it is hard, it means that there is a proper resistance that is coming from the material. It means that it is good in compression because it is resisting more. High compressive strength means resistant to deformation under compressive loading, right? So that is the reason why, of course, this is wrong. Okay, so this is how the question is simple, looking simple, but the concept wise they are trying to test you in different varieties. You see here they are trying to test it in drilling. This is in machining. This is in machining, and this is somewhere in some material properties, right? So it's very important to know everything, right? So I mean, of course you don't know everything, but know the maximum is best. So if you have the maximum knowledge, then you will be able to get into the uh, company, I mean the post, whatever you are applying for. Okay. So next, complex irregular three-dimensional surfaces can be located using the following method. Ha. So this again comes under the principle of locations. How you locate a material and place it and fix it. Jigs and fixtures. There you'll be discussing all these things. Okay. So generally, in GATE syllabus or some in normal examination syllabus, they just say jigs and fixtures, but they won't discuss all this sighting, nesting, all these buttons and all. They won't discuss in depth. But yeah, so if you're preparing for engineering service examination, then this kind of things will be detailedly covered in the syllabus. But yet again, the question is little kind of an out of syllabus. But yes, they said jigs of fixture, then you have to know everything about jigs and fixtures. And one more problem here is until unless you see it, you won't be able to remember it. That is a problem with manufacturing. Okay. So fine, let's discuss what is what. If you know, it's good. If you do not know, no worries. I'll be discussing. Good. So let's see what is sighting, nesting, integral locators, buttons, and all. Then we'll see. We'll come to the question and see which is the right option. First, we'll discuss the options. Okay. Let's not read the question first. First, we'll discuss the options. First, let us understand the options, and then we'll discuss the question. Take the right answer. First, we'll discuss what is sighting. Okay, this is sighting location. I've put the diagrams, then it will be easy for me to explain more if the diagram is already present. Okay. So what is the sighting? Sighting is what is sight? Looking, right? So it's a simple operation for location. What is that? You have some plane objects, right? You have seen this. This is some kind of a plane object, right? And this is what is your bottom plate, and this is what is your object that you're placing. But what is location? Location means you have to place it at right location, right? So this is where for very simple components by just visual inspection you are putting it. Sighting plane is there. Some lines are present. You have to match that lines and put it. That's it, right? So these are for for very simple components. For simple components. And also for very bigger components. Okay, so the workpiece is placed on a plane such a way that there is some equal margins on all the sides. Okay, that's it. This is very simple. Okay, next is the nesting. What is this nesting? Uh, if you have a very you see there is some kind of a very this is a bolt which is not very simple. It's having very good turns here and there, all these things. Now this you have to place it onto the jig or fixture that you have. So this is the component, and this is what is the fixing device, right? So the nesting, whatever it's called here, it's called nesting locator. Whatever these things are nesting locators, they say. Okay, so these are outside the surface. So the locators are already present. So this is corresponding to the same point. So the nesting locators are there. Locating means like principle of location means locators should be there. No, you have to have some reference points. Those are called locations, right? So nesting involves some some complicated shape only, of course. So the this shape, or sometimes this is also known as nest, can be used to precisely position the part, right, into some three-dimensional spaces. So this is a three-dimensional object, right? Some different. If you look at this direction, some cross section, this direction, cross section, some different things. So it is for some three-dimensional irregular surface only. So what I'm saying is that simply having some kind of nests or some kind of a locators which are on the surface of it will be able to identify and put it onto the right position, and that is called nesting. Nesting is for not for simple components, it's for some complex 3D objects. Okay, good. And it needs some multi points. You see, some multi points are there. Good. Next. Next is, okay, this is nesting, don't forget. And this is integral locators. Integral means internal. That's it. Okay. So these locators are built into the part to be machined. So these locators are already into the part. It is not on the surface. You're just putting some marks. You're making some machining into the part. Okay, this is the part to be machined. Part, and some machining is already occurred here. Okay, machined in the part, and that is what is locator. Locator. Okay, so that's why it's called integral locators. You have already machined the part for the location. That's why it's called integral locators. Good. Next. Next are buttons. I think, yeah, it is buttons. Buttons and pins also they say, but buttons. These are buttons. So these are some kind of simple surfaces only. You are just make a hole, put the button. Make a hole, put the button. That buttons are for identifying and locating it. That's it. And of course, these buttons will not support some simple structures only. It won't be supporting some high level structures. Okay. So now let's go and see the question and answer the right one. Complex irregular 3D surfaces can be located using the following method. Sighting, simple. We can't use it because we have seen that. Nesting, yes. Integral locators, you have to have some integral location. For a complex objects, making machining is not easy. So obviously this is not a good option. Buttons also we cannot use for some complex irregular items. Hence, nesting is the right answer. That's it. Okay, good. Now, in tolerance of a part, unless otherwise specified, individual features of size must not violate size limits of MMC. What is MMC? Maximum material condition. Okay. Okay. So the maximum material condition we have to discuss. First, what is maximum material condition we have discussed, because okay, here whatever you are trying to see, the LMC is least material condition. Okay, now we'll discuss. First, we'll discuss what is maximum material condition. Maximum material condition, nothing but, for instance, if you say there is a hole, maximum material condition will say that smallest diameter. Smallest diameter means what? Maximum material condition. Obviously, no. There is a hole like this. Bigger hole. See, this is the material, right? Material. Hole. In the same material, same tube or whatever it is, same dimensions. If you make more hole, you're removing the material, so you're lessening the material, right? Small hole, more material. Big hole, less material. Right? So that is what the maximum material condition they say. It's like opposite of what we're discussing. So if you have gone through the concept of the tolerancing or geometric and dimensioning or whatever it is, right? There is a principle called envelope principle. Okay. What does this envelope principle say? Envelope principle says, or it's called envelope requirement, principle or requirement. What does it say? It says that the surface of a size, I mean, of a part. So the size must not violate an envelope of perfect size and shape. Okay, how can I say this? Okay, I'll write it. So surface of a part should not vi- violate uh, an envelope. Okay, envelope of form. What is this form? Form means size and shape. Size and shape have to be not violated, and that is the principle of envelope principle or the envelope requirement. Okay, so this has to not be violated. Now let's go and read the options and see what does this say. In tolerancing or geometric tolerancing or geometric dimensioning, whatever it is, unless otherwise specified, individual features must of size must not violate size limits of mmc at any cross section. They're not saying anything about that, right? Right. So if maximum material condition is not about violating any cross section, or but about defining size, right? Where the features contain maximum amount of material. It's not about that. Sorry, it's about that. Sorry, it's about defining the size and maximum material. It's only discussing about the material. It's not discussing anything about the limits. So that's why obviously this is not the right answer. Not violate an envelope of perfect form at LMC. We are discussing this in the terms of MMC, not in the terms of LMC, right? So obviously this is not the right answer, right? Surface part should not violate envelope form of size and shape, right? So not violate an envelope perfect form of MMC. Yes, yes, this is the right answer. See, you might think that why not the upper option? Because in terms of maximum material condition only, we'll be discussing this envelope and all these things. We won't be discussing in the context of LMC. That's why C is the right answer. Okay, good. So maximum material condition will ensure machining if there is any mistake, or if it is going as per specified dimensions or not. We'll understand that. The envelope principle that I'm telling, no, it should perfectly maintain. Okay, good. Frictional shear stress tau in metal forming is expressed in as, okay, this formula, if you remember, it's good. If you do not remember also, you can derive, but it will take so much time. I think you should remember this. So this they are asking in the terms of metal forming. So if at all you have attended our classes, we have discussed these things in terms of the initial stage of our metal forming classes. We have discussed two criterion: thrust cast maximum shear stress criteria, and Warsmeister's, that is maximum distortion energy criteria. There we have derived the maximum the what do you say, the yes, yield stress in we are relating the yield stress in shear and yield stress in tensile loading, right? So we'll relate them and then we'll be relating them to the shear stress. So let's understand some interesting concepts here. Okay, so as we are discussing about friction, there are two type of frictions that will be visible in metal forming. Okay, so let's write what are those. So in metal forming, there are two frictions: sliding friction and sticking friction in metal forming. Okay, sticking friction. Okay, so sliding friction is given as as here talking about friction. As friction is there, then there are these frictional stresses that are developed, and that frictional stresses developed are represented by tau. We'll call it even this as some shear because it is parallel to the surface, right? So it's kind of like some Coulomb frictions that are proportional to the pressure, right? So pressure means normal force. Let's say if you have some block like this, and if you are moving like this, the backward direction is your frictional force, and this is your normal force, something like that. Fine. Anyways, so now, or sometimes people even write as some uh, normal pressure P. That is the pressure that we are applying. What we apply is, of course, mg is equal to n, right? In the same way. In sliding friction, this tau is equal to mu into p, where mu is coefficient of friction, static friction. In sliding friction, this tau is equal to some m into k, assuming, and this m is what is called friction factor. This m is what? Friction factor, right? So generally, in some cases, they assume m is equal to 1. When the layer is sticking to the die, something like that. They'll say the conditions, and they'll say it is equal. If it is having no lubrication in higher friction conditions, most of the contacting part may be slipping, and it is sticking. There are so many things. So that's why they are not taking m is equal to 1. Okay. So if you understand this concept, then let's go and discuss some other concept called uh, the the relationship between the yield stress in tension, yield stress in shear. Please try to understand. In tension or tension only, yield stress in shear. Okay. According to Tresca's criteria, you derive You have some three-dimensional thrust cast. Tau max is equal to the maximum stress minus minimum stress divided by 2. All these things you do. According to Tresca, we write tau max, the maximum shear stress will be equal to the shear stress in yield. Okay. And there is another criteria, that is von Mises criteria, right? Von Mises, maximum distortion energy criteria, right? Here they say that there is some kind of plastic deformation that is occurring when strain energy is reaching its critical value. All these things. Let's not go into depth. We are not discussing. We are not here to discuss all this stuff here. So, according to Tresca's criteria, if you just want to relate these two, then you'll get sigma y. Okay, sorry. I'll write k is equal to sigma y by root 3. Okay. And according to the sorry, sigma y by 2, sorry, it is 1 minus root 3. Okay, 2. For 1 minus k is equal to sigma y by root 3. Derivation is easily done. It can be done. If you want, you can visit our lectures. And sometimes I think this derivation is even available in Gaussian Malik book. Okay, it is available in Gaussian Malik book. You can try to go back and read it. Okay. Now with these two concepts, let's go and attack our problem. What is that? Frictional shear stress tau is equal to, you know that it is m into k. What is m? Frictional shear factor. That's what frictional shear factor, right? And what is m? And this sigma bar is mean flow stress. Mean flow stress can be assumed to be sigma y. So this sigma star is sigma y generally, not every time, in some conditions. Okay. So now which one is right? So obviously you can see, you can substitute sigma y by root 3, right? K is equal to sigma y by root 3, right? So m into sigma y by root 3, or you can write m into sigma bar by root 3. Which option is making sense? Of course, first option is making sense, right? So this is the answer. Okay, very good. Hope you understood the derivation, and not derivation, the logic behind it. Good. Next, in CAD, okay, yeah, suddenly we went to CAD. The geometric transformation is expressed as P star is equal to some matrix into P, where T is transformation matrix. If the matrix T is diagonal, then transformation is called. This is simply CAD. If you have taken some CAD course, or maybe if you have read the CAD topic, this is a straightforward problem for you. But anyways, we'll discuss each and everything, and then we'll come back to the question again. Okay, so we'll discuss about translation, we'll discuss about reflection, rotation, scaling, and a common notation where the transformed uh, uh, point or the transformed geometry is equivalent to some matrices into the original point or the original geometry. The P represents the original one. This is a transformed one, and the transformation is happening through this T. And T is a matrix. Okay. So let's see what is translation, reflection, rotation, and scaling. Okay. So in general, the transformations, whatever they're saying, this P star is equal to T into P. P is original point. P star is transformed. Okay. So based on this transformation matrix only, all these things will happen. Okay. So this transformation matrix is 4 cross 4. whatever this transformational matrix I'm saying, no, it is 4 cross 4. In that 4 cross 4, first 3 cross 3 belongs to rotation matrix. First 3 cross 3 will belong to rotation. 3 cross 3. This is called rotation matrix. And next 3 cross 1 will give you translation matrix. This will give you perception and this will give you scaling. Okay, good. So if you want to find out the translatory thing, then the T should be active and rotation matrix should be identity matrix, and perception should be straight away zeros, and scaling should be straight away 1. Okay, so in scaling or when scaling, I'll write what is this. R is rotation matrix, that is 3 cross 3. T is translation matrix, translation that is happening, that is 3 cross 1, and the total is 4 cross 4. Okay, and P is perception. In which angle you're looking? Perception. This is 1 cross 3. And S is scaling, it is 1 cross 1. But here, in terms of whatever they're asking is little different. We'll understand what is this. Okay, so forget about this notation. If you want to find out translation, right, what will happen? Let's take some point X star, Y star, and some Z star, right? This is some kind of a matrix. So as we have 4 cross 4, we have to have one more extra. That is what is your one you're appending for making ease of calculations. Okay. So then we have some rotation matrix that should be 1 0 0 0 1 0 0 0 1, and perception should be 0 0 0. Translation should be 1 1 1, or maybe some translation that you want to have. Let us say it is some translation in x direction, translation in y direction, some translation in z direction, and scaling is 1. If you multiply with your the sorry, this is 4 cross 4, so you'll get it like this. You will not get like this. You'll get it column 1. This is star, y star, z star, and 1. This is the original P star, and P will be some original one, that is X, Y, Z, and 1. So this is P, this is T, and this is P star. Okay. So if you do that, you'll get X star is equal to X plus Tx. You do the multiplication, you'll get the same thing what I'm doing here. Y star is equal to Y plus Tx, Y plus Ty, and Z star is equal to Z plus Tz. So it is translating. You are moving the point in some translatory X, translatory Y, and translatory Z. So, but here in this question, they're asking where T is a diagonal matrix. Diagonal in the sense only diagonal element should be present. All the elements should not be there. Any element should not be there. Only diagonal element should be active. Okay, so that's the reason why this is not the right answer for our question, because off diagonal Tx, Ty, and all these things are having some values, right? So hence this is not the answer. And next is rotation, right? So rotation is what is R. This R can have 3 different matrices. Rotational matrix along R theta x, R theta y, R theta z. So it will have different sine theta, cos theta, sin theta, all these things will be there. Here also off diagonals are present, off diagonal elements are present. I'm not writing it, you can go and search it. Elements mt will be present. So but this is not the right answer, right? So rotation also is gone. Reflection. Let's discuss about reflect. Reflection. Yes, we'll discuss about reflection. So in reflection, okay, let me write one rotation matrix, man, for your for your happiness. So it is uh, cos theta. Some I think it is minus sine theta. I don't remember, it is sine theta. Yeah, sine theta minus sine theta cos theta 0 0 0 0 0. This will be 1. This will be 0 0. Of course, this will be 0 0 0, and this will be 1. So like this, you can write for this and this. You can write some values. Okay, and this will be multiplied to your original point like this here, and then you get the rotated point of the transformed point. Okay, here also you can see a diagonal of the diagonals are minus sin theta is there, sin theta is there, of diagonal elements are present, and hence the answer is not right. Right, whatever we are thinking is not right. And for reflection, right? Reflection, what is that? It's kind of a mirror image. Okay, here we will have only, okay, let's say if we are having reflection about, we want to have about x, then your t matrix will be, I'll write directly, then your t matrix will be x, right? So x will be minus 1 1 1 1, and rest all are zeros. 0 0 0 0 0 0 0 0 0 0 0 0, like this. These are having some diagonal elements, but the diagonal elements are not same, right? Diagonal matrix means diagonal element should be same, right? Hence the oh, not diagonal elements. I'm not saying diagonal elements. Sorry, sir, 1 minute. What are they saying? The T is a diagonal. Then transformation matrix. If T is diagonal, then the transformation is called. I think it is reflection. Okay. If there's an ambiguous, okay, I will discuss it. So okay. So we are talking about the scaling here. Okay, good. Okay, so in scaling, what happens? How will the scaling look like? The If you see the scaling matrix, that Sx at the end will be there. Okay, let me write the scale. Okay. Right. So if you want to do the scaling matrix, uh, you have some identity matrix here: 1 0 0 0 1 0 0 0 1 0 0 0 0 0 0, and sx as scaling. This is scaling, and this is what is the right answer, right? You just multiply this scaling value to whatever this point is there. So the scaling will happen in to the every point. Okay, because you multiply this into this into this into this, so the scaling will happen to the points separately. Equivalently, the scaling will happen. The scaling is used where when you are zooming and zooming out, the scaling will happen. So this is the diagonal matrix, right? So hence the answer is scale. Okay, I hope I've confused a little bit here because it's a big theory. So hope you go back and read some kind of theory on the transformations. There are shearing operation. There are so many operations actually. So it's difficult for us to discuss all things for this one question alone, right? So just do your theory and research and come back and you'll understand what is the right answer. Okay, good. Which one of the following is permanent mold casting process? Permanent, right? So casting molding techniques are of two type, right? So one is permanent and one is not permanent, right? So What is that permanent and not permanent? In the sense, like if you can reuse the material of the mold cavity. If you made the mold cavity, you made the mold cavity, and the mold cavity you can use it again and again without destroying it, right? Then it is called permanent mold cavity. Okay. So investment crashing process. Are you keeping the mold cavity permanent? No. Why? Because how does this investment crashing process will progress? First, what you will do? You have some dies. You have some dies. Some dies are there. Some dies are there. You inject wax into it. Inject wax, and the die will be having some shape. You'll inject wax, and that wax will take the die shape, the internal dimensions of the die, and wax will get solidified, and the part is wax part is formed. You take that wax part. Let's say if the wax part is something like this. You take it, and this is wax. Okay, this is wax. Now you coat it. Coat it. How you coat it? You dip into one slurry. Dip it into slurry. Wait for some time. Some kind of coating is formed. Again you dip, again you wait for some time, some extra thin layer of coating is formed. Like that you dip for 3-4 times, and something some extra thin coating is formed here. The coating is formed here, like this. The coating is formed on the wax pattern, right? After coating is done, what you do? You heat this complete object. Then wax is melted out, and you drain the wax out, and making this shell. Shell will be like this. This is shell now. Wax is drained out. Now you pour liquid metal into this. Now you pour liquid metal into this. Once you pour liquid metal into this, then you solidify the liquid metal and you break the shell. The shell was the mold cavity, right? Initially, so you're breaking his shell. So it is not it is not permanent mold casting process. Obviously, no. Full molding. What is full molding? Full molding is nothing but you are making your pattern is some plastics, some lightweight or low density plastics or polymers, lightweight, where instead of removing the pattern out and then assemble it and pouring, what you do, you pour directly onto the pattern itself. Your the molten liquid, you pour directly onto the pattern. Then that whatever the pattern is there, the pattern will get burnt because it is having light density burnt, and then it will go into the atmosphere through vapor, right? And then it is creating some passage to the mold cavity, and then the metal liquid is filling into the mold cavity. That's it. And now you want to remove the part. No, again you're going to break the mold cavity. Sand molding only you're using. There also you have to break it again. Okay. So hence this also is not right answer, because you have to break the mold. It's not a permanent mold casting process. Vacuum casting process. Nothing, man. You're just putting this in the vacuum and you're doing it just for avoiding some kind of impurities and all this stuff, atmospheric contamination, everything is there. No, you're putting it in vacuum and doing it. Anyways, again you have to remove it. The only place where you reuse your mold cavity again and again is die casting. Die casting, where mold material is directly pressurized into the die. There are cold chamber die casting, hot chamber. All these things are there. You pressurize it. You solidify. Again, you remove it. Again, you close it. Again, you do it. So you're not destroying your mold before some iterations of molding process. So it can be done for some high complex shapes, and the volume of production. The production rate also is very high because you are not destroying it again, forming it, destroying it, forming it, destroying it, right? So hence, permanent mold casting process is die casting process. Okay, very good. Next, identify the geometric characteristic that describes the feature geometry and interrelationship of the parts. So there are some different terms that I have mentioned. We'll discuss one by one and see what is right, which suits better to this question. Form tolerance, form, orientation tolerance, and dimension. What is form tolerance? Form tolerance will specify how much the geometrical feature can deviate from its ideal shape. Okay, so determines deviation from not size, shape, ideal shape, like cylindricity, circularity, flatness, straightness, sphericity, profiles, right? Whether it is happening, involute profile is there, whether involute profile is meeting properly or not. Profile only, shape wise, they are saying, they're not talking anything about dimensions. This is also a circle, this is also a circle, but this is having some radius r1, this is having some radius r2. But both can be circular. If both are perfect circles, then it is proper, it's having proper form tolerance. Even the dimensions are not matching to the designed value. Okay, so that is what I'm talking about. Sphericity, say cylindricity, circularity, right? Maybe straightness, flatness, all these things will come under form tolerance, right? So what is the question? Identify the geometric characteristics to describe the feature geometry and interrelationship of the part features. This is nothing to do with the internal part features and all, right? Okay, I'll write example here. It is like some example is flatness and cylindricity. Better I'll write that two value things. We'll understand what I'm trying to say. Okay, so this is flatness or cylindricity. Example, so on, so on, so on, so on. Next is form. What is form? Form. This simply they give form. Form refers it's the shape. Form means the shape. It's a simple shape. So how come simple shape will have will describe the feature of geometry and interrelationship of the parts? It won't say anything about that. What is orientation tolerance? Orientation tolerance will control the orientation of the features. How, I mean, relative to the feature, in which direction we can orient, whether we can put it perpendicularly, we can put angularly, whether it's a parallel to each other. Now, as we are talking about perpendicular things and angularity and all these things, then it doesn't with respect to what it is perpendicular, with respect to the part features itself, right? So obviously, this is the right answer. It's talking about the feature geometry and the interrelationship between the part features, whether they are perpendicular to each other, whether they are angular at some point, whether they are perpendicular to parallel to each other, like that, right? So when it is talking about perpendicularity and parallel angularity and parallelism, then orientation tolerances will be. That is the meaning of orientation tolerance, because it's discussing with the orientation and interrelation features it also are being discussed, right? So I can write the example here, perpendicularity example, perpendicularity and hence etc etc etc. Right? Dimensions are, what is the dimension? It's some kind of a size of a geometry, some specific value of size of a geometry. It doesn't describe anything about geometric interrelationship between the features. Simple size of a feature, size of a part of feature. Feature in the sense like whether straight, circle, whatever it is. So answer is C. Okay, good. Next. Datum features on the part are, okay, permanent, temporary, either permanent or temporary. So what is datum? First, what is datum? A datum is kind of a reference identity or reference entity, I can say. Okay. So let's say if at all you have some kind of a liquid, some liquid, then you say, and this is placed on a table. Then the height of the liquid, then you can say what is the height, the fluid is floating at the top point of the pressure at this point is P1. So you want to measure some kind of these things at this point one. Okay, not right. Let's not point. Oh, yeah, it's point P1. Okay, that's good. So we need a datum. We need a reference, or we can say this is the datum. This is the datum, or maybe we can say this is the datum, right? So datum will is the reference, something like that. It could be some kind of a surface. It could be some kind of a feature. It could be anything. Now they ask you whether this datum is permanent or temporary, right? It cannot. It can be permanent also, right? Some kind of part geometries are there, which are very standard in nature. For that, the datum is fixed with respect to outer edge. Maybe there is some kind of a this thing. So there is some drill that you're with respect to outer edge. There is some kind of datum that you're fixing it, and it should be in that place only. That is fixed. Sometimes it can be temporary as well, right? Because based on the conditions, the labor that not the labor, the worker who is working will be fixing his own datum and doing the work. Like when we discuss the two systems, like absolute system and the incremental system in CNC machining, G and M codes. When we discuss G and M codes, there we'll discuss, right. If you write G90 and G91, G90 corresponds to the absolute system and G91 corresponds to the incremental system. You can do anything. It can change it. The datum is changed. So I feel the answer could be either permanent or temporary based on the situation. It is not fixed that yeah, datum is permanent or datum is temporary. It can be anything. Okay, good. Root opening of a single V groove weld joint of plate thickness T is. Okay. So yeah, so this is a standard question, but we'll discuss what is single V groove joint and all these things. So this is what is a single V groove joint. So these are your welding plate. These are your plates, or these are sheets, whatever it is, plates only you can call. This is somewhere I've taken this stainless steel 316 grade. Okay. So this is what is your root opening. You have to have some gap between that. That is what is your root opening, and this is the thickness of your plate, right? Thickness of your plate, plate thickness. Plate thickness. So what they're asking the question, whether the gap between this in terms of this thickness T is T by 3, T by 4, T by 5, T by 6. Generally, they take it as T by 4. That is the convention. We cannot. There are so many reasons behind it, but they take it as T by 4. Okay, according to the standard rule, I'm telling it. So there is no way that we can say why and all. Maybe we can go dwell deep into the subject and understand the significance of root opening, the strength, the bonding, and all these things. Then we'll be able to understand why it is T by 4, why it is not T by 3, and why it is not T by. Based on several experiments, also they might have concluded, yeah, this is T by 4, like that. Okay, fine. So, anyways, the answer is T by 4. You have to remember that. Good. Okay, so just give me a 1 minute. I'll just come have a sip of water and come back in 1 minute. I I'm coming. Yeah, I'm back. Good. So, am I audible? Okay. Hope I'm audible. Okay. Good. Now they're asking the next question, that is, cubic B-spline curve requires minimum dash control points. First, we have to understand what is cubic B-spline curve. What is B-spline? So they in CAD, in computer aided design, again I'm telling you, in gate and all, this B-spline, Bezier curve, they very often, I mean, I think they didn't ask also. So the syllabus is quite extensive according to the questions that they're asking. I see the syllabus is very extensive. You have to have a very good grip on the basic knowledge. It's not about the formulas. You write some, solve some equations based on the questions. I feel that yeah, the questions are superficial, but on a broader sense, you have to know the broader level rather than the deeper level. Okay, so let's see what is B spline here. Okay, a B spline is nothing but a piecewise continuous uh, 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 polynomial of some degree, right? So piecewise continuous means like these are your control points. C naught is your control point. C1, C2, C3 are your, they say, control points. C1, C2, C3, C4, and all etc. are control points. They say control points. Based on your control points, the curve will change accordingly. So we'll first answer the question and go into depth. What is B-spline? Okay. Or first we will define what is B-spline curve, and then we'll see what is the answer. Okay. So B-spline is nothing but it's given as some function f of t or f of x is equal to summation of I is equal to 1 to n pi into bi. So I'll write ni because bi is for Bezier curve. It's a Bunsen polynomial. Ni I'll write. Ni is some kind of a basis function, I can say. So it is defined by this. These are control points, and this is your basis function, and these are your number of points, number of control points. Okay. So if you want to find, you want to take some kind of cubic B-spline, how many points are required? How many control points are minimum control points are required for a cubic B-spline? So we'll take just simple normal curve we'll take. Let's say if it is some, let's say this basis function is recursive and all, forget about it. It's recursive in nature actually. So don't get into that complicated things. It's little advanced to whatever the level that we are discussing here. So let's say if there is some kind of a cubic function. So cubic function can be written as x cube plus some x squares plus some x plus some constant c. Some constant c. So let me write this is c. Okay, maybe I will write this is c1, c2, c3, and c4. So this is some function x. So to fix this curve, how many constants are required? 1, 2, 3, 4 constants. For solving this C1, C2, C3, C4, how many points are required? 4 points are required because four unknowns and four equations have to be found. For four different equations, 4 points have to be required. And that is the reason why here we need for cubic B-spline, because this is the cubic degree, we have to have 4 control points. So coming to this B spline, there's a progression that is happening. Right? The progression is nothing but first They have some cubic polynomials, simple cubic polynomials, what we have written here, right? Then we have Bezier curves. Bezier is a German guy, curves. And then we have B-spline curves, even surfaces also, but we are discussing in the context of curves, right? And the B-spline has been extended to NURBS. NURBS are nothing but non-uniform rational B-splines. So there are some things called knot vectors. These knot vectors are having non-uniform values, and you're rationalizing at the end to represent some conic sections. So there is a big area opening there. It's computer aided design, basic computer aided design. Okay, so let's not go to depth. So as a simple basic understanding, we need some 4 control points to define a cubic B-spline curve. That is very important to understand. Good. Next, the reaction in which a liquid phase transforms into a two different solid phases is called. Okay, there are 4 reactions here as given. So these are all belonging to the iron carbide diagram only. Okay, so let's go one by one. So where the reaction is happening? The reaction is happening at this point. Let me put red point. This is where one reaction is happening, right? And this is where one reaction is happening. This is where one reaction is happening. Let's discuss all these 3 reactions, and then we'll discuss something about that. Okay. So let's see what is what. At this point, it's I'll write 3 different colors. That would be good for me. Yeah, that's a good idea. This is some point. This is another point. That is where the transition is happening. Okay, that's the reason why I'm writing it here. So at red point, what is happening? The gamma austenite is converting into alpha plus some perlite, right? Okay, so this gamma is solid, this alpha is solid, and this perlite also is solid. Solid to two different solids. That's why this is called eutectoid reaction. Eutectoid reaction, because this is hypoelectric, this is hyperelectric, because of that eutectoid reaction. Next, we'll take the another ink here, and then we'll discuss at this point. Oh, sorry, we'll discuss, yeah, at this point. That is, okay, 1 minute. I think, yeah, what I'm writing is right. Some reactions, no, not this reaction. I think, let me write the other reaction here on there, where it is converting as. Yeah, let me write this. Okay, I'm also a little here. So let me write this reaction, liquid to this gamma. So liquid to that is liquid iron to the austenite, that is gamma, plus Fe3C, that is cementite, right? And here it is going from a liquid phase to 2 different solid phases. Okay, okay, good. So, and this is what this is called peritectic reaction. Peritectic reaction. This is called peritectic reaction. Okay. Liquid to I think, am I not this? I think somewhere I'm not. This is eutectic reaction, man, not peritectic. Yes. Sorry for this. eutectic. Tick. Okay. So liquid to two different solids, eutectic reaction. Okay. And there is one more reaction, that is peritectic reaction. Okay, that is I'm not showing where it is solid to two solids, solid plus solid 1 plus solid 2, giving rise to new solid. And this is peritectic reaction. Peritectoid reaction. Right? And another is peritectic reaction. That is also important. Peritectic reaction. Nothing but solid phase plus liquid phase giving rise to back and forth, giving rise to solid phase. Okay, so let's remember this. So we'll go to our options. The reaction in which a liquid phase transforms into two different solids, liquid to two solids, is eutectic. Solid to two solids is eutectoid. Liquid to two solids is eutectic. Two solids to one another solid is peritectoid. Solid plus liquid giving to solid is peritectic. So this is the option for us, that is eutectic. So I'm writing this as eutectic. Okay, so it is little confusion. Even I also little here and there names are little, terminologies are little confusion. So you have to be very cautious and understand the concepts and have some kind of a memory power to make sure that you're not making mistake with the names, not the concept. Concept you should not memorize it. Concept you have to understand it, but name wise you have to memorize and make sure that you do not make mistake or confuse with the name here. Okay, good. Margin wear in drill is due to. First, we'll discuss what is margin wear. Okay. So first, what is margin? First, what is margin? This is a drill bit. So this margin wear will be happening in the drill bit. Okay. So the wear is happening at this point. You see, happily they are showing it. I've taken a right book here. So the wear is happening at that margin. So this is the margin. This is the margin. Then they're asking why this margin wear is happening. Okay, is it due to abrasion? It is due to vibration. It is due to thermal softening or diffusion. So okay, first is what is abrasion? Abrasion is nothing but if two objects are rubbing against each other, and if there is a good, if there is some kind of the coefficient of friction between, or if there are some kind of rough surfaces between the two objects that are being rubbed, then that is called abrasion. So when you're putting drill bit into your workpiece, we do not know whether it is the surface is abrasive or it can be softer also. Right? So that will not be the answer for the margin wear. Margin wear is happening here at these things. That is where the hard hitting is happening. Tuck, tuck, tuck. So that is where the drill bit is coming in contact with the workpiece and where the chips are coming out through these flutes. These are called flutes. Flutes. Why these flutes are provided? These flutes are provided to help the chips come out through their culls. Otherwise, where will the chips go? Right? That's the thing. So it's not due to vibration. Vibration of machine, because of vibration, how this will be disturbed? Vibration of machine, maybe the workpiece dimensions will be disturbed. Eccentricity is produced in the workpiece. What is eccentricity? If circle is like this, we are making like this. This is called eccentricity. Because some movement is happening, and or maybe the dimensions are increasing in the circle. Right? If you're making a circular hole, the dimensions here and there are offsetting, and that is why it's called eccentricity. Or maybe the hole is offset, or maybe the dimensions of hole are not in perfect size and shape. Right? That is called eccentricity. So vibrations will give the eccentricity in the workpiece, not some margin wear. Yeah, thermal softening is making sense. What is thermal softening? Diffusion also, see, thermal softening and diffusion will happen at high temperatures. So first we'll discuss about what is thermal softening. Thermal softening is nothing but at higher temperatures, the uh, the workpiece, whatever we are machining, because when we are machining, when we are drilling, the drill bit is rotating with some RPM, some 2000 or maybe some kind of 1000 RPM rotations per minute. In a minute, it is rotating 1000 times. It's very high speed RPM, right? So when you are rotating it, there's a huge temperature that is generated between the workpiece and the tool, because it is rotating, right? Rotating. Because of that high temperature, some kind of smoothness is happening of this material. You know that like when high temperatures are reaching, the workpiece becomes softer. As it is becoming softer, maybe this part is getting worn away. Okay, because the hardness gradually, uh, what do you say? Uh, the hardness will reduce as the softening is happening, right? So that is the reason why this wear is happening. Okay, so yeah, thermal softening is one of the answer. But what is diffusion then? Diffusion is nothing but, so initially you alloy it. Why you alloy it? You alloy the material by infusing carbon, some boron, some hydrogen, not hydrogen, some nitrogen, all these things you'll put it to make the alloying element, to make the things harder. Now, as you machine, the temperature is very high. So what is diffusion? Diffusion is nothing but the movement of higher concentration atoms to lower concentration atoms. It's nothing but if there are some atoms which are higher concentration, very dense, and there is some lower concentration here. The movement of higher concentration to lower concentration at high temperatures is called diffusion. So as the process is happening, it might happen that the small atoms in the tool, why this fusion is happening, because carbon atoms are very much present in the drill bit, because carbon makes the drill bit stronger. So at high temperatures, it's a possibility that the concentration difference of carbon atom in the drill bit and in the workpiece will be different. In the drill bit, the concentration will be high. In the workpiece, the concentration will be low. That's the reason why workpiece is softer. Right? As you drill it, the concentration difference is there. At high temperature, maybe due to concentration difference, carbons are getting transferred to the workpiece, and as transformation or mass transfer is happening, which means that the wearing is happening. So that is having the least probability for this kind of margin edge. So the margin edge is because of the thermal softening, not the diffusion. Diffusion also will occur at high temperatures. Thermal softening also will occur at high temperatures. Okay, good. Now, next. The smallest thickness can be measured by a slip gauge. So this is a standard question. If you know something about slip gauges, then you can answer it. The answer is like this thing. So there are some kind of some 48, no, some 64 something slip gauge blocks are there. So in this, if you see, the smallest one is 0.01. The standard one, there is nothing to be explained here. So the answer is A. Okay. Next. Thumb rule between feed and nose radius in rough turning is, okay. So if you are knowing something about nose radius, then you'll be able to understand what is feed and nose. Okay, they're discussing in the context of the cutting tool. Okay, so if you see the top view, the tool will be some kind of bent like this, and this is what is your this thing, and here you can see some kind of a radius. That is what is called R. R is your nose radius. Why you are giving this nose radius? Why it is not sharp? Because if it is sharp, the it will increase the surface roughness. Because please assume like this: if you have a pencil, if you have sharpened the pencil and you're putting your pencil onto the book and writing it, then you can see the indentations on the back side of your page, because it is very sharp that it is disturbing the roughness of page. If you have a blunt pencil, that kind of indentation will not be able to, you will not be able to look that in the backside of the page. It is a little blunter, right? So this nose radius should be optimal when you're machining. Why? Because if you are having a very smaller nose radiuses, smaller is some good amount of optimal nose radiuses will reduce the vibration of the machine, will ideally increase some kind of speedness of the machining, right? And surface roughness also will be good if you have optimal range of nose radius. If you do not have optimal range of nose radius, if you're increasing the nose radius, then the material removal rate will not increase and will decrease, as well as the cutting forces will increase, and also the vibration of machine will happen. Some shattering of machine will happen, right? So the optimum nose radius is important, not high or low. Optimum value is important. Optimum nose radius is good. Okay. So what is the question here? They're asking the thumb rule between the feed and nose radius. Generally, feed is equivalent to nose radius by 2. That is a thumb rule. There is no other option. You have to remember this. Good. Now, let's go to the next question. Specific metal cutting energy is expressed as, oh, this is the formula. So let's derive it, man. So actually you have to remember it, but I'll derive it. Okay, let's derive it. Let's take time for 5 minutes and discuss about it. First, we'll start discussing what is specific metal cutting energy. What is specific metal cutting energy? So I'll write specific cutting energy. Metal is common, right? Specific cutting energy. We'll write what is specific cutting energy. Specific cutting energy is defined by some U. U is nothing but amount of energy required to remove unit volume of material. Again, I repeat, amount of energy required to remove unit volume of material from the workpiece. Okay? So, amount of energy required by volume of material removed. Okay. There is another concept, that is MRR. We know that material removed rate. That is volume of material removed divided by time. So MRR, what is the volume of material removed? Length of cut, width of cut, thickness of cut divided by time t. Length of cut divided by time is velocity, cutting velocity, VC. Cutting velocity into width of cut can be written as depth of cut. Thickness of cut, uncut chip thickness, is also known as feed. This and all we have discussed clearly when we are discussing the machining. If you don't understand why width of cut is depth of cut, why uncut chip thickness is feed, you have to go and listen to our lectures. Okay, it's a very important and beautiful thing that is being explained in that, because the questions have been asked. Simply they'll give width of cut, but they won't give depth of cut. But depth of cut is width of cut, and why it is that happening, in which conditions it is happening. So that and all are discussed in our lectures. If you want, if you're interested, you can get our lectures and view them. Okay. So here you can, yeah, I'm writing from here. Okay. So what is energy of energy? What is energy cutting force? Energy can be written as some kind of uh, um, energy, but energy. 1 minute. I'm getting a call. 1 minute. Sorry. 1 minute. Okay, sorry for the interruption. Okay, what is energy? Okay, I'm writing energy in terms of what I was thinking. Energy in terms of power. What is energy? Energy by time is power, right? So I will divide the numerator and denominator with respect to time. So energy by time, volume of metal removed by time. Energy by time is power, and volume by time is MRR. Simple. Okay. What is power? Power is nothing but cutting power. Cutting power. This is cutting power. Cutting force into cutting velocity divided by MRR, cutting velocity into depth of cut into feed. This get cancelled. F by depth of cut into feed will give you the specific cutting energy. From here, so we have the formula. Specific kinetic energy is expressed as, but we have this formula. They're asking this formula, and please remember this is cutting force, cutting force, cutting force. If you remember in the previous session, or the before this previous session, somewhere around, we have discussed the relationship of cutting forces in using merchant circle diagram, right? So that was the resultant force is the frictional force divided by sine beta, where beta is your friction angle, normal force divided by cos beta, right? And that is equal to thrust force divided by sine beta minus alpha. Alpha is rake angle, right? Remember, we have even seen how this has come. I've told you, right? Please go to our previous sessions. We'll be able to understand why how we got this, right? And this is FC cutting of force divided by cos beta minus alpha, and force perpendicular to the shear force divided by a sine, sorry, divided by sine phi plus beta minus alpha. Yes, sine phi plus beta minus alpha. Beta minus, that's phi shear angle. Okay. Then this is Fs divided by cos of phi plus beta minus. So here they are saying tau is shear stress. Okay, this tau is shear stress. So shear stress means you have to take the relationship between these two, right? So let's take that. So Fc by cos beta minus alpha is equal to Fs by cos phi plus beta minus. What is shear stress? Tau s is equal to, we know that tau s is equal to Fs. We have even seen this, Fs sine phi, shear force sine phi divided by the thickness of cut into width of cut, and this thickness of cut into width of cut can be written as feed into depth of cut. We have been seen here. They have taken what? Okay, they take anything. We'll take that, no problem. So it is feed into depth of cut, and that is tau s. So from here we can get Fs, and all we can get the cutting force. Why? Because we want cutting force divided by df, right? So we substitute Fs is equal to tau Fd divided by sin phi. Substitute that here. So Fs Fc by cos beta minus alpha is equal to tau s Fd by, sorry, by sin phi, right, by cos phi plus beta minus alpha, right? So from here, this I'll send, oh, okay, I will send this side. So Fc divided by F to D is equal to uh, this tau shear stress into cos beta minus alpha divided by sin phi into cos phi plus beta minus alpha. So of course this is your specific cutting energy, and this is the answer. This is a derivation. Tau is cos beta minus alpha by sin phi. Tau is cos beta minus alpha. Tau is cos beta by sin phi, divided by cos phi plus beta minus alpha. Cos phi plus beta minus alpha, isn't it? Cos 5 plus beta minus alpha. 5 plus beta minus alpha. Answer is A. That's it. Okay, this is the derivation. Okay, next one. The missing dimension in the following part is simple. We have discussed we can use the rule of propagation or we can use the maximum minimum distance. So what is the maximum distance? Okay, let me do it here itself. So they're asking this distance, right? So what is the maximum? This is 57, right? Here max is 57 plus 1, that is 58, and minimum is 57 minus 2, that is 55. Very good. So for all the things we'll write, okay, let's write maximum dimension and minimum dimensions. So maximum dimension of that missing part, okay, that is what is important. So what is that? 58, because we are taking the maximum. 58 minus, right? So this is, so for this AB to be maximum, this should be minimum. That is important. Okay, 17 minus 1 is 16, right? And 11 minus 1 is 10, plus 11 minus 1 is 10. So plus what is this? 17. Okay, 18 and 17 and there, it is 17. 17 is the minimum, right? So I've taken the minimum plus 17. If you do this, it is 43, 43, 52, 40, 50. Minimum dimensions you can take. Okay, that is 55 minus the maximum of the upper ones, 17, 11 plus 1, 12, and 18. So this will be 29 plus 18, 8. So now let's see the options. So maximum dimension of the missing component is 15. 11.5 plus 1.5 is 13. This is 7.12.5, 13. And oh, okay, this is 11.5 is 12. 13. This is 14. This is 15. Yes, this is the answer. That's it. That's it. This is the answer. Okay, let's minus subtract it. 11.5, 11 minus 3. 11 minus 3 is, yeah, 8. Good. That's it. 8. That is the answer. Simple. Okay. So 11 plus or minus 3.5 is the answer. From options, we can directly go ahead. Next. Which one of the following is false about boronizing process? What is boronizing first? Boronizing is nothing but, if it's called boroiding also is another name. Boronizing is having another name called boroiding. It's infusion of boron, man. That's it. I'll tell you. Right. It's a surface hardening process where boron atoms are diffused into the surface of workpiece, and where the hard surface is created by this boroid bonds, boroid atoms, boron atoms, not boroid atoms, boron atoms. So which is good for high wear resistance and toughness. Or chemistry. Okay. So when boron is applied, okay, they're asking which one of the following is false about boronizing. Oh, okay. Is it used for packed cementation process? Yes, it's true for packed cementation process, where you can see the workpiece is packed in a boron environment, and then You can heat for some higher temperatures and then allow the boron diffusion to happen, and all these things will happen. So obviously, pack cementation is right. It can be done only on high carbon. No, this is wrong. No, we can do it on low carbon steels also. It can be done for everything. It's not only. This is the problem here, right? And this is the answer. This is the answer. But let's see the other options as well, because we should not take any chance. It is used to obtain extremely high wear. Yeah, I've already written it. High wear resistance. So already it is true. So this is true. This is true. It leads to high distortion. Uh, Yeah, okay, yeah. It is the negative. Yeah, boronizing process. Now, what happens if you're not doing it in a controlled way? If you're not doing this boronizing process in a controlled way, then it can happen. Yes, it can happen. This is right. So this will happen. Will happen when uh, uh, when boronizing is not controlled properly. Okay, boronizing is not controlled properly. Okay, next. What type of locator used to prevent jamming during the locating pins? So there are some locating pins. What are the locating pins? Concentric locator, integral locator, equilateral locator, and spherical locator. Locators are some kind of a ball. Spherical locator is a ball locator. It will be like this. Okay. Concentric locator is nothing but we have some datum, and then we'll see whether the concentricity is there, and we'll fix the position of circular, especially for circular things. Okay. So this spherical locator, no, there's a big advantage of it, because the contact between spherical locator and the object is point only. You try to touch sphere at any surface, you try to touch sphere on anything, at least for a flat surface, no, the point of contact between the workpiece and the sphere locator is very less. Okay, point of contact between workpiece and sphere locator is less. Spherical locator is less. That's true, na? Right? So that is the reason why, as the contact is less, how jamming will happen? Jamming will not at all happen. This is the answer straight away. Okay, good. Ha. Maximum reduction in rolling processes. So if you go to rolling, let's see. Okay, this is your rolling, and this is your radius r, and this is your thing, and this is your theta, right? Angle of roll here, and sorry, angle of bite. It's not roll. Angle of bite. Theta is angle of bite. Oh, did they take theta? Alpha. Okay, let me write alpha. Better. Angle of bite. Biting, because rolling, the roll is in contact with, this is roll workpiece. Right. It's going like this, and rotating is happening. The rotation is happening like this. Sorry. Yeah, it is in reverse direction. Okay. So if you have the inlet thickness is some H2 and sorry H1, the outlet thickness is H2. So delta H is H1 minus H2. Okay. And if you see, this is R, that is d by 2, radius of roll and diameter of roll. So the reduction, what they're talking is delta H. The reduction, the formula is already derived. That is d into 1 minus cos R. That's it. You have to remember this. Derivation, I'm not doing it. You have to remember this. Reduction, diameter of roll, and alpha is angle of bite. That's it. This is the formula. Pick the right one. First, d by 2, d by 2, d by 2, remove it. Option at all is not there. No option. Very good. Answer is next. White iron structure consists of. So we have discussed about this white iron in one of our previous sessions, where they were asking about the variety of cast irons which has maximum hardness. So we have discussed about malleable iron, gray iron, white iron. In the previous session, please go and check. We'll know it. And we also discussed white iron is known for its hardness. White iron is known for its hardness, and also it is having the hardest constituent of iron, and that is what is cemented Fe3C, hard and brittle. This is the answer. We have discussed all these things in the previous. Perlite is not harder because it is having alpha iron, which is softer, because carbon percentage is very less. Okay, not that. It is Fe3C, that is cementite. Okay, good. This is a good one. So load was displacement curve in the following figure pertains to. So it's not only this. We'll discuss so many load curves and discuss which one belongs to what. So as mentioned, the y-axis represents load and x-axis represents the distance as we push the metal forming. In metal forming only we're discussing. Okay. So the first one belongs to a closed die operation. Closed die forging with flash actually. Why with flash? What is flash? Flash is nothing but the cushion effect. You put some extra space for the material to go inside. Just go and see the diagrams of flash. Okay, you understand what I'm saying. So because of that compression, the flash will give you some cushion. And that is the reason why it looks the curve, because the cushion is giving, and after the cushion is filled, it is going up as we are sliding it. And this is upset forging. Open, this is closed die. This is upset forging. Because as you keep on moving, that the load will keep on increasing as you keep on increasing the displacement. And this is your extrusion, forward and backward here written, so it is extrusion. And here you can see initially there is increment, and there is nothing increment in load. Displacement is there. Again, there is an increment in the load. This is called bending operation. And this is sudden increment and sudden decrement. It means that it is happening in fraction of minutes. Okay, fraction of seconds. Sorry, in fraction of seconds, something is happening. So that's why it's called blanking or punching. Blanking or punching, anything is fine. Blanking or punching. And this is coining. Keeping on increasing, keeping on increasing. Finished. So in the diagram, they're showing something like this. And this is extrusion, bending, blanking, coining. Of course, this is blanking or punching. Answer is easy. Okay. Next. The process in which the lower tolerances in the cast product of ferrous and non-ferrous material can be achieved. Okay. So we'll discuss each one of it. So first we'll discuss about die casting. Die casting, while die casting, die. Okay, this cold chamber, hot chamber also, this tolerancing at all is very bad because of the sticking of the element to the cold chamber and with the hot chamber, and this and all are die it is permanent mold, right? Die casting, just now we have discussed, it is permanent mold, right? So obviously the precision is very bad, right? So we cannot achieve lowest tolerances. Tolerances are very bad in die casting. So obviously this is not right. Shell casting. The shell casting is you make the shell and then you okay, yeah. So this is precise, but not as precise as investment casting. Sand casting also, this is a very bad precision. Sand particles are already the sand inclusions also will be present onto the metal solid that you have solidified. Okay, very precision is not at all good. Investment casting is known for its precision, but cell casting also is good, but not as good as the investment casting. So lowest precision means higher, lowest tolerance means highest precision is achieved in investment casting. That is the reason why these are used for jewelry and all medical instruments, and all these things will be the applications where investment casting is being used. Okay, next. Pickling treatment is cleaning the casting with. So actually, the casting can be treated with so many things. Soda ash, dilute acid to compressed air and sand particles are in shots. So the last two are not for cleaning purpose. Those are for yeah, it's for cleaning purpose, but it is on the mechanical perspective. It's not pickling. Pickling means you are cleaning some kind of dirtiness. Okay, dirtiness, which is like some kind of a corrosion is there, some kind of corrosion environment is there, and some kind of rust is there on the item, and you want to remove that rust. So then you'll be using either soda ash or dilute acid. So soda ash generally is used for so chemical. It's used in some kind of chemical industries, not in machining or maybe in metal manufacturing industries. Okay, so the pickling is nothing but it's some kind of an solvent or some kind of a material where you solution is some kind of a solution where you put it onto your workpiece, and it picks up all the surface impurities like rust, some corrosion things will be there, right? So they'll be cleaning and descale the steel or the material with dilute acid, and this dilute acid can be anything. Generally it's some kind of inorganic contaminants, they say, right? So they'll remove some inorganic contaminants, they say. Okay, so dilute acid will be a right answer. Soda ash, it's sodium carbonate. Actually it is not nothing but sodium carbonate. Generally I think it is not used for cleaning the casting. Okay, so it is like dilute acid that is used for cleaning the casting, which is corroded. Compressed air and sand particles are generally for cleaning the surface for abrasion. This is abrasion where some kind of you know sand particles that stuck to the metal surface will be cleaned. And iron shots is not at all for cleaning; it's for improving the uh, uh, mechanical properties, like improving the uh, mechanical properties. Right. Next, elements which make stainless steel stainless. Oh, what a good question. So, in stainless steel, the important component itself, you have to know this, is chromium. And magnesium at all is not present in stainless steel, right? Carbon is present. Nickel sometimes some addition is there. Magnesium at all is not present. Okay. And chromium is very important because what will happen? Chromium, when you add chromium into the steel, the chromium will form chromium oxide. Okay? That chromium oxide will float on top of the part. Of the sorry, let me write it again. Will float on top of the part on top of the part. Okay. Float. And this is very important. This chromium oxide, whatever I'm saying, is good for extremely corrosion resistance. Extremely corrosion resistance. Stainless steel is known for corrosion resistance, isn't it? Right? And also, it is having its self-repairing repairing capability. If at all it is scratched, right? Again, oxygen is there, chromium is there, chromium oxide is formed. Again, scratch also will be easily covered up, right? Chromium makes the stainless steel stainless. Okay, very important question. Nice question. Okay, so yeah, I think we are done with today. Yeah, we are on time. Very good. So, but industrial questions, some 3-4 questions were there we couldn't discuss in this session. So hopefully we'll combine it in the next class, and I will discuss all the questions in the next class. Okay. So as of now, we have completed 2015, 2016, 2017 one, and 2017 two. There are two more question papers that are left: 2019 and 2000. No. I think 2019 and 20, or 18 and 19. I don't remember. There are some two more question papers. So we'll be discussing. In this part, we have only discussed manufacturing. The industrial part for 2017 two, we are going to discuss in the next class. Okay. Okay. Thank you guys for listening to this lecture, or viewing the recorded lecture. If at all you have any doubts, please do comment on the comment section. I'll be able to respond them wisely. Thank you.